Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. Steam jet ejectors, working principles, performance analysis, types of ejectors and applications. In this video course, you will learn the working principles of steam jet ejectors, performance analysis, applications and advantages, single stage and multi-stage ejectors. Please subscribe to the channel. By subscribing, you will motivate us to produce more knowledgeable video content for your career progress. So subscribe now before you forget. Steam ejectors, also called jet pumps, are equipment that are used to create and maintain vacuum in distillation columns, evaporators, dryers, and reactors, and other processing units. A steam jet ejector is a simplified type of compressor that has no moving parts. Steam ejectors are used as independent equipment for pulling vacuum in systems to which it is connected or in combination with condensers and with liquid ring pumps to achieve higher vacuum in the process system. Applications of steam jet ejector. A steam jet ejector has two main applications in petroleum refining, petrochemical and process industries. The first major application is to produce vacuum in process systems. The other application is in the heat recovery system, which is essentially an energy optimization requirement. Steam ejectors used in production of vacuum constitutes the largest segment of ejector application. This segment covers varieties of industries, including refineries, petrochemicals, and other process industries and power plants. Several crude distillation units, distillation of products with low relative volatility, and distillation of heat-sensitive products are carried out under vacuum. Working principle and analysis of steam jet ejector. Ejectors use motive fluids at high pressure to create vacuum. Liquids, air and steam are usually used as a motive medium. Steam jet ejectors use steam as a motive medium. The ejector uses the pressure energy of the motive fluid to suck the gas and compress it to the discharge pressure. How does the ejector make it happen? Let us move on to find out with a sketch. The ejector consists essentially of a nozzle with converging and diverging sections. The motive steam enters the steam chest and expands through the nozzle. The high velocity steam jet discharging from the nozzle develops a low pressure and sucks in gas or vapor from the vessel to be evacuated. The evacuated gas or vapor is entrained by the steam into a diffuser in which a mixing of both fluids takes place. The diffuser is shaped like a venturi with converging and diverging sections. The mixed fluids are recompressed to an intermediate pressure by conversion of the velocity energy into pressure energy in the diffuser. More pressure rise occurs along the discharge cone as flows slow down. The final discharge pressure is lower than the initial motive steam pressure, but higher than the suction pressure. The key operating parameters are Pm, the motive steam pressure, Ps, the suction pressure, Pd is a discharge pressure or the back pressure to the ejector, mm, the motive steam flow, ms, the suction flow, md is a mixed flow at discharge. In the jet ejector, there is no volume displacement as happens in positive displacement compressors. Instead, it is a momentum transfer device. mm times um plus ms times us equal to md times ud. The md is equal to plus ms, which is the mass of motive stream plus the mass of gas sucked in. The above equation, is equal to velocity of the motive fluid. us is the velocity of the gas at suction, and ud is the velocity of the mixer at the discharge. The pressure profile across the steam jet ejector is illustrated in this figure. The process step 1 to 2 is the expansion of the motive steam in the nozzle from pressure P1 to P2. Step 3-2 is a suction of gas from suction chamber. Step 2, 4 and 5 is the mixing, compression and discharge, and the pressure increase from P2 to P5. Pressure P3 is slightly higher than P2 due to the pressure drop between the suction chamber and nozzle. For all calculation purposes, that can be treated as equal. The velocity profile can be analyzed in the same way. The velocity of the motive steam increases from V1 at the inlet of the ejector, that is point 1, to the maximum velocity V2 at the exit of the nozzle, that is point 2, and then starts to increase to V4 as the steam moves into the mixing zone of the diffuser. The velocity of the suction gas V3, which is normally equal to V1, increases to a maximum as it is sucked and entrained into the steam, and then decreases to the same velocity V4 as the gas mixes with the steam. As the mixer flows through the diffuser, the velocity progressively decreases until it drops to V5 at the discharge end of the ejector. The drop in velocity from V2 to V5 is accompanied by increase in pressure from P2 to P5. The usual design concept is that the motive fluid jet issuing from the nozzle at supersonic velocity entrains the inlet gas stream and raises its velocity to sonic velocity as the two flows mix at the diffuser throat. The mixed flow exits the discharge at subsonic condition. Entrainment efficiency. The expansion of motive stream in the nozzle and the subsequent recompression of the mixer in the diffuser are isentropic processes. Due to turbulence, the entrainment of the low velocity suction gas by a high velocity stream results in loss of kinetic energy. The kinetic energy of the mixer that remains is only a fraction of that possessed by the original motive fluid. The fraction that is successfully transferred to the mixer through the exchange of momentum is referred to as entrainment efficiency. The fractional quantity of kinetic energy lost by the motive fluid is converted into heat and is absorbed by the gas mixer. The result is increase in enthalpy of the mixer. Since the ejector nozzle is a fixed unit equivalent to a fixed orifice, any change in motive steam pressure leads to reduction of mass of motive steam. Hence, steam jet ejector of a given design has optimum efficiency and maximum capacity at specified motive steam pressure, suction pressure and discharge pressures. Hence, variation in these parameters will have an impact on the capacity of the ejector. What happens when the motive steam pressure is decreased? A reduction in motive steam pressure decreases the ejector capacity. The steam consumption is an important performance criteria of the steam ejector. This figure shows a typical performance curve of steam jet ejector. For a given motive steam pressure and discharge pressure, the suction vapor flow is a function of the suction pressure. As the absolute suction pressure decreases, the suction vapor flow capacity of the ejector decreases. The quantity of vapor or gas evacuated also depends on the compression ratio CR, expansion ratio ER, molecular mass, and suction temperature. The expansion ratio ER is defined as the ratio of motive steam pressure to suction pressure, which is equal to Pm divided by Ps. The compression ratio CR is defined as the ratio of discharge pressure to the suction pressure, which is equal to Pd divided by Ps. The higher the value of ER, the less will be the motive steam required. But higher the value of CR, the more will be the motive steam required. Motive steam pressure control. Before we move on, I would like to make a call to my dear viewers. Your SPEC e-learn channel is one-stop learning and skill development destination for your career needs. Get instant access to useful career-oriented subjects and become knowledgeable and competent. So do not forget to subscribe. Please press the subscribe button now. Since the performance of the steam jet ejector system depends on the motive steam pressure, variation of steam pressure could impact the vacuum system performance. Hence, it is recommended to use a pressure control valve on the motive steam line to steam jet ejector. This scheme illustrates the ejector package with the motive steam under pressure control. Ejector is designed for 10 bar pressure. Any increase or decrease in pressure will impact the ejector performance. The steam pressure control valve will prevent that. This scheme illustrates the ejector package with motive steam controlling the vacuum chamber pressure. The vacuum or the absolute pressure of the vessel under suction is controlled by motive flow at the design steam pressure. How to make specification of steam jet ejector? The steam jet ejector vendor or supplier or manufacturer develops a design once the end user provides the process data. The specification parameters needed for the supplier to design the steam ejector includes the following: suction pressure needed, motive steam pressure or temperature, discharge pressure, suction flow, temperature and composition, cooling medium, pressure and temperature for multi-stage ejector. Types of steam jet ejectors: single stage versus multi-stage. Ejectors may be of two types, single stage and multi-stage. Since the capacity of a single ejector is fixed by its dimension, single unit has a limitation on its compression ratio and throughput that it can achieve. For greater compression ratio, two or more ejectors are needed in series. For greater throughput, two or more ejectors can be arranged in parallel. In multi-stage systems, condensers are used between the ejector stages to condense the steam and vapors removed. Only the non-condensable from the top of the condenser of the first stage is routed to the next ejector stage, thus reducing the load on the next stage of ejector. So, a condenser of an ejector system reduces the amount of vapor load a downstream ejector should handle. The condensate is removed from the bottom of the condenser into a hot well. The thermocompression takes place progressively from the initial suction pressure of the first stage to the final discharge pressure in the last ejector stage. A single stage ejector will produce pressures in the range of 65 to 1000 millibar absolute. A two-stage ejector will produce pressure in the range of 30 into 130 millibar absolute. A three-stage ejector will produce pressure in the range of 1.3 to 33 millibar absolute. And a five-stage ejector may be required to produce pressures in the range of 0 to 0.01 millibar absolute. A three-stage steam ejector package discharging into atmosphere is illustrated in this figure. The condensate from the condensers flow to a hot well located below the ejector package. In the ejector package, the vapor velocities in the interconnected process piping must be kept very low to reduce the pressure drop in the piping. Otherwise, it will increase the compression ratio for the ejector stage. The minimum size of the interstage piping should at least be equal to that of the inlet piping to the first stage. The height of the condensate drainage leg. The height of the condensate drainage leg is also an important design factor. It is common engineering practice to keep the entire ejector package in the same floor and allow the condensate to drain by gravity to the hot well. In such case, the pressure in the first stage condenser determines the height of the drainage leg from the condenser bottom to the hot well. The height of the drainage leg is given as HD equal to 10.2 divided by specific gravity minus 0.0102 P1 divided by specific gravity plus HF plus HS. Where HD is the height of the condensate drain leg in meters. P1 is the first stage suction pressure in millibar. Hg is the specific gravity of the condensate. HF is the head loss due to friction in the drain leg in meters. HS is the seal height in the hot well in meter. The seal height shall be kept a minimum of 0.3 meter. If the condensate is only water, then the above equation with the specific gravity equal to 1 becomes HD equal to 10.2 minus 0.0102 P1 plus HF plus HS. If the friction loss is neglected, HS equal to 0.3 meter, then the jet system operating with a first stage condenser pressure of 10 millibar absolute will require a drainage head of 10.49 meters. If this condition is not met, the condensate will not drain to hot well and the condenser flooding will occur. The condensate drain leg should be laid out vertically down with no bends in between. If there are constraints in running the pipe vertically down right up to the top of the hot well due to fouling by other equipment, then the line can be sloped 45 degrees at such intermediate position. The condensate collected in the hot well flows over a baffle to the pumping compartment located at one end of the hot well, from which the condensate is pumped out. It is recommended to install a pressure gauge at the process inlet of each ejector stage to monitor the ejector performance. Icing may be observed in the low pressure stages due to fall in temperature of the steam below the freezing point due to the isentropic expansion of the steam. This is a normal phenomenon and there is no reason to worry. Advantages of steam jet ejectors. Steam jet ejectors have several advantages over other vacuum producing devices. Ejectors are easy to operate and have low installed cost, but the operating cost is very high as large amount of steam is required. Absence of moving parts makes the ejectors practically maintenance free. The ejectors can handle practically any type of vapor or gas, including wet and dry gas mixers. The main advantages include low cost, no moving parts and hence no maintenance, compact construction, reliability, suitable for vacuum up to 0.1 millibar absolute, can be of corrosion resistant materials. Please subscribe to our channel and get updates on the upcoming courses by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. With this, we have come to the end of the presentation. Please give your comments, if any, about this course after you finished viewing this video. Share with your friends and colleagues to reach out to large number of career-oriented professional students. Thank you for watching.